Thank you again, and thank you for coming back from the coffee break. So I left you with this question before. So in spite of the fact that we have built up all our framework to produce molecular hydrogen, which is necessary to produce the collapse of the first stars, yet the cosmological content, what we could do, what the universe could do purely at the mean density level was not enough. So this density of 10 to the minus 6 particle per cc in molecular hydrogen was not clearly sufficient to induce the formation of the collapse of the perturbations. Now, in all, as we were saying before, in all this treatment, what is lacking is the fact that we have not included structure formation yet, and structure formation is dominated by the presence of dark matter. So dark matter fluctuations grow constantly with time. They don't go through this oscillatory behavior that matter and radiation follow. And so because they grow, they become nonlinear, and they create what we know as dark matter halos, right? So this kind of spherical symmetry structures that are gravity bound. And so because those form and are in place, they force the baryons to fall in their potential well. And so that helps a lot to our problem, because remember that we are struggling to get more H2, okay? So that has to come from the spherical collapse of the perturbation. Now, we have seen this morning that the spherical collapse is a simplification, because probably this is not fully spherical. But, you know, at the end of the day, all axes will eventually collapse and to form a more or less spherical structure. So let's work under this hypothesis now. And so if you make this simplified assumption, then there's a well-known analytical solution that we can use, at least as a guide, to solve our problem. So the analytical solution to the spherical collapse is essentially as simple as this tiny equation here. So this is the density with respect to the background mean, the one through which we have computed all the reactions before, and is a function of a single parameter alpha that is related to the virialization redshift and any arbitrary redshift by this relation, which is not linear, but is also simple. So we can, as a function of redshift through alpha, we can compute what is the increase of the density in the collapse structure as a function of time of redshift. So the growth of this perturbation continues up to it reaches what we call the virialization density, rho vir, essentially where that is given by a simple number, which is 18 pi squared times the mean density. And this is what we call the virialization density. This comes from the solution of the problem plus the notion of the phenomenon that we call virialization, which is essentially a readjustment of the orbits of dark matter particle to go in equilibrium with the prescription of the virial theorem. All right, so now we have how the density grows as a function of redshift, or time if you prefer. And so we can write the thermochemical evolution of the system, which is nothing else. It's a complicated word to say the first principle of thermodynamics. And that means that the internal energy change, okay, this is the internal energy, kT over mu mp, the proton mass, as a function of time, is determined by the compression work, so the PDV work that is here, minus the famous radiative losses that we had discussed before that are encapsulated into the lambda function. The lambda function, as we have seen, depends, yes, on the density, but also depends on the abundance of the species that we have to produce the, for example, molecular hydrogen we have seen before. So together with the energy equation, we also need to add the chemical equation that describes the abundance yi of different species. And here in abstract form, we are representing one particle, two particle, and three particle processes. Okay, so we have all the processes that we have discussed so far: formation, destruction of molecular hydrogen, and other species. So it's very complicated. As we'll see later, these are something like 500 species that you have to follow if you want to do a proper job. Okay, so these are the equations. So the problem is solvable. And so if now you include the fact that because of the spherical collapse, the density of the gas increases because it's falling into the potential well of the dark matter. And while the density is increasing, also the rates of formation of molecular hydrogen increase. So you can form more hydrogen than we had to start with, which was the 10 to the minus 6 particle per cc. And now this extra amount of molecular hydrogen creates a hole in our cooling diagram. And you see this hole here that was not present before. So you have to compare this with the previous figure. It was this. So this is only with the residual, cosmological residual or relic fraction of molecular hydrogen. This one is with the molecular hydrogen that halos, the dark matter halos help the gas to produce. And so now the region, remember that the region in which we are interested here is where the cooling time is much shorter than the free fall time. These are reported again. So this is the cooling time, and this is the free fall time. We want the cooling time to be shorter than this. And so by doing the proper calculation, you see that you find here a hole where now there is a space for some of the perturbations to being able to produce enough. Yes?
Quick question. Does the dark matter collapse first and then the gas falls?
Yes.
Or do they fall together?
The dark matter perturbation grow first because in the linear regime, at least, the radiation and matter still oscillate. So dark matter instead continues to grow all the time, apart from a small period at the end of the radiation-dominated epoch. But in the matter-dominated epoch, they always grow.
Second question is the gas, when it falls in, or the hydrogen, is it shocking? Is it supersonic?
Yes, it's virialized at this temperature, at the temperature of the halo. So in that sense that we were saying before, it's compression plus shocks. And so it's virialized by the fact that it's transforming the gravitational infall velocity into a temperature. So it's thermalizing this motion, and it goes in equilibrium with the halo with the dark matter halo at the same virial temperature determined by the mass of the dark matter halo. So you see here that there is a sweet spot that corresponds to roughly virial temperatures of 3,000–4,000 K and a redshift between 20 and 30. Okay? So that is as a rule of thumb, this is the place where we are supposing that the first stars form. So halos with virial temperature of 10 to the of 4,000 K roughly, and redshift between 20 and 30. Now, this is based on these arguments. Now we will see if this is true or not, but certainly it's a guide to search for these stars or which objects these stars are formed into. Now, keep in mind that if you transform a virial temperature of 4,000 K at redshift 30 into a mass, what would you expect? Can you do your intuition? I know you can do the calculation, but what would you expect? What type of masses? Halo masses of what?
Can you say the numbers again?
Virial temperature 4,000 at redshift 30. 10 to the 6, I've heard. That's perfect. Yeah, it's about 10 to the 6 solar masses. And this is a halo with the galaxy, okay, in it. And so this is the same size of a molecular cloud in our galaxy. molecular clouds in our galaxy are 10 to the 6 solar masses. So you see where the problem of galaxy formation is entangled and almost indistinguishable from the formation of stars in molecular clouds, but with the only, as we see, fundamental difference that in this case, dark matter plays a fundamental role. Because without dark matter, we wouldn't ever produce such a collapsed baryonic structure. Okay, so this is the important thing. Okay, now
The very right part of the plot.
here, the
Above, around.
here.
Yes.
Oh, this in order to populate this, you would need to have some perturbations that are 15 sigma or something like that. So basically, there's one object in the universe. Maybe it's there. Yeah, you're right. But extremely, 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 extremely rare. Now, there's something, a complication that I want to fly over because we don't have much time. But there's another thing that could change the situation is that in addition to molecular hydrogen, there's another molecule that could potentially play a role, which is HD. So a molecule in which you have substituted one hydrogen atom with a deuterium one. And so not only this is the second most abundant primordial molecule because it has abundances which are 1% or less than H2, but however, you can balance this lower abundance with a higher dipole moment because it's an asymmetric molecule, and therefore the transition probabilities are higher. So the result is that while with H2, you can provide cooling, but only down to a certain temperature. Remember, hydrogen can only provide cooling, have transition down to 10 to the 4K. But this is because this is the range of the admitted by the transition of neutral hydrogen. The same for molecular hydrogen. You don't have transitions that can be excited in a gas which has temperature below 500. So typically, you cannot cool the gas below 500 K or something like that. But with HD, which has closer transitions, then you can go down to roughly 100 K. So, of course, you may wonder where, so you can create cooler gas. And that, as we will see, has important impact on the mass of the first stars. Because we will see that the mass of the first stars is probably related to the temperature of the gas out of which they form. So if you can cool it, then you can have lower mass population 3 stars. I don't want to go into many more details. I'll just tell you that you can form HD behind shocks. And this is interesting because we have seen that during the collapse, as we were discussing before, during the collapse you can have shocks, and so behind the shock, basically, so if you have a shock wave that is standing here, so this is the pre-shock gas and this is the post-shock gas, so the shock is traveling this way. So behind the shock, you have the formation of various species like D plus and D, and also HD formed by this reaction. So D plus H2 goes into HD plus H plus. So you form some HD provided you have a shock. So if during the collapse you also have shocks, then maybe you can decrease the temperature. So this is, as I said, is an addition to our scenario before, but it may be important in some circumstances. So just to recap, this is the first part of the lecture or the first chapter. So cooling function drops at 10 to the 4 if you only have primordial gas. So in that case, the galaxies cannot cool and form stars. The H2 molecules come to rescue, provided you have some molecular hydrogen, which is formed and dissociated in gas phase rather than on dust, okay? In primordial condition. And so the cosmological abundance, though, is not sufficient. But however, due to the presence of dark matter, the abundance can grow. and lead to a true collapse where you start to form stars. So that was the essentially the first part of the chapter 1. Now, okay, now we are in this situation in which we have built up a dark matter halo, mass of 10 to the 6, redshift 30. Let's keep this number as our fiducial numbers. And so we want to ask, what is the nature of the stars that form out of this situation? What can we say of the stars that have been formed in this situation? So to do this, we can proceed in different ways. One way is to resort to numerical simulations, and these have been attempted in the last 20 years in various flavors and with various prescriptions. So this is one rendering of such results. So what I'm showing here is some images that correspond to a very small region of the universe, only 12 kiloparsec, Kobuvian kiloparsec. This is because we want to look at the formation of the stars. So we are bound by numerical resolution to select very tiny biased regions where we know that the first stars, that the condition that we have discussed before can occur. And then we follow this region to higher and higher resolution. So here is redshift 100, and so the top line, the top row is gas density, the bottom one is dark matter density. And so these are 3 redshifts, 100, 24, and 20. So first of all, you see that the process that we have discussed before leads to the formation indeed of an almost spherical dark matter halo, in which there are, that you see from here, this is dark matter, that contains at the center a very enhanced gas density, a clump of gas that potentially could lead to the formation of stars. And then you have filaments here that you see clearly. By the way, you see that these two figures should be the same, right? Dark matter and baryons are somewhat different. So can somebody explain to me why? These two figures are not the same, right? There's no ionization radiation in the, yes?
Floor temperature is higher for the gas, and that matters for the pressure.
What is the temperature of the dark matter? I see many hands here. Please, in random order, so speak.
Maybe because the virial can be compressed, while the dark matter cannot. This is why the filament appear much thicker with dark matter.
I would say just the opposite. They are thicker in the gas, and they are thinner in dark matter. You see this? This looks like an out of focus representation of that, right?
The white panel seems to be a little
This one?
more thinner.
No. No. For example, look at this. There's a filament here that you don't see here. There's not even a filament there. Okay, corresponding to these ones.
Okay, so it's the reverse here.
Yeah.
It's due to what you have.
Let's listen another attempt.
I mean, my guess would be that because dark matter don't really interact with anything, the gas would be easily spread out, or like
Spread out by what?
by like just dissipating in the
Dissipating what?
space that it's in. I don't know.
But dissipating what? What is the subject of the what is it that is dissipated?
The heat.
So you think it's cooling, but if you dissipate, it would collapse.
Or maybe energizing.
Next attempt. Sorry. Yeah, suction.
Is of the baryons itself is not allowing it to collapse.
Very good suction. Yeah, where do you come from? Okay, good. All right, that's very good. So you must have. Yeah, this is the correct question, right? Because dark matter is pressureless, so it's zero pressure. Well, because there's no interaction among dark matter particles apart from gravity. But the gas has pressure. And so the pressure prevents the collapse. So it opposes the collapse. This is it's a very important point because it will come back later. So that's why I wanted to make it clear immediately. So yeah, this is the reason. So pressure counteracts the effect of gravity. It's the enemy, okay, for gravity. Well, for us, not so sure. Right, so yeah, so we do simulations like this. And yeah, this is we can take this as a starting point for our simple layman analysis of what is going on, because I want to tell you what we can learn from basic physical principles rather than, interpreting this simulation. And there is issue also that the simulation can get up to a certain point. So we can't get from the simulation down to the formation of a protostar. Okay, so not so far at least. And so we still need to understand the physics so that we can perhaps also make better simulation in the future, or at least try to understand the process from first principle. Now, you think that this is something very modern, but it's not, because it dates the solution of this problem, of what is happening to this core of gas and dark matter in that situation, how it will evolve, was already investigated in 1965. Okay, so probably not even your parents were born at that time. And so this is called the Larson-Penston solution, by the name of the two people that developed this solution. And the solution is an isothermal collapse, so even isothermal. So they don't even try to include all the possible difficulties of dealing with the cooling function. They say, okay, it's isothermal, even though it could be generalized to an adiabatic relation between pressure and density. And so they just simply wrote the Eulerian formulation of fluid dynamics in this limit. Now, as much as you can think that this is naive, it gives you the actual answer, even though not in a quantitative sense, but in a qualitative sense, is perfectly correct. So, a few equations. I think that after coffee, they're good, because they allow you to go back to reality. And so reality is tougher than we think, but not so much. So we have three equations here, which I think you should recognize. This is the conservation of momentum, conservation of mass, and this is the mass definition. So for those of you who have done stellar courses, these are essentially the same thing that you solve for stellar evolution. And so the momentum equation is U is the velocity, m is the mass of the cloud, r is the radius from the center, a given temperature, which is kept fixed, and rho is the density. And here, again, mass and mass conservation and mass definition. So the basic idea that Larson and Penston is where these equations are too difficult to solve, so let's find something to simplify them. And the idea was to use a trick that is to separate variables. So, for example, velocity in general is a function of radius and time. And they said, okay, but let's assume that they are separable. So you have a function b, which depends on time, and a function u, which depends on space, s. S now is the radial coordinate normalized to some factor, a, which is only a function of time, which, for those of you which are in love with cosmology, should remember something, right? So these are comoving and physical coordinates, the same thing, right? So you have that this is the physical unit and this is the comoving with the fluid. The only thing is that when we deal with cosmology, we have an expanding Hubble flow. Here we have a contracting collapse core of a star, but physics is the same. Okay, so with this trick, they went on. Keep with me for another slide of things of equation, and then everything will become more simple. This is a bit technical, but I think the solution is so nice that it's amazing that they could find a way to solve it. So with this assumption, they the coefficients in which you separate the variables must satisfy some mathematical constraint that depend on the nature of the equation, of course. But then you substitute into the equations, and the momentum and mass conservation equation take this form. And also, then what they did is just to normalize the equation to some physical quantity. And you can recognize this quantity here. What is it? Square root of RT, where R is the gas constant. Is the velocity, is the sound speed in the gas, okay? So the sound speed, for example, space is normalized to sound speed times tau, which is the derivative of the scale factor. So think it as the Hubble time. So this is sound speed times the characteristic time scale of the collapse. And the same, the velocity is normalized to the sound speed, and then we have the eta, which is essentially the mass in non-dimensional units. This is the solution. Okay, it means nothing, but as you will see, it makes sense. So you have to apply boundary conditions because there are infinities here. So you need to show that whenever the denominator goes to 0, the numerator also goes to 0. These are a bit technical, but important. So you have all this. Read the paper by Larson, 1965. It's beautiful. Well, to me, it's a very nice piece of work. So we have that solution, which is here. But for us, it's a little bit still opaque. Okay? Let's try to simplify it. So let's look at limiting behaviors at very large distances. So x is much larger than 1. So we are looking at the external boundaries of the cloud that is collapsing. And so there, the limit of the, for x much larger than 1 of the velocity goes to 0. And for the density, it goes to -2 as x goes to infinity. So here we have a plot as a function of distance. So this is the center. And so this, you're going to larger and larger distances. So this limit corresponds to things that are somewhere here. Okay? And in fact, we see that the velocity, which is this curve, goes to a flat value at infinity, and then it drops at the center, while the density has a behavior like r to the -2, and then becomes flat. So the interesting thing about, and the very physical information that this solution is carrying, is that the cloud, while it is collapsing, it's adjusting to a profile which is a core plus an envelope. So you have a central core with density which is basically flat, and then an envelope that is r to the -2. And the velocity is almost, the gas is almost at rest very far from the center, but then it falls down. You see the velocity becomes negative, and it falls down into the center. And so the size of this core has a very special value because it has the size which is comparable to what we call the Jeans length that I will introduce more formally in the next slide. But it means that there is a region here of flat density. Can you explain me why? Why is it getting, why this thing is not going like this? Why is it not continuing to go to infinity? Why the density is not continuing to increase like r to the -2 down to the center? Yes? Exactly. So exactly what we were saying before, right? It's gas pressure, because when you're trying to compress the gas, by compression, the center becomes denser and denser, and if you allow the temperature also to increase, also, this is an isothermal thing, remember. But the increase of the pressure, decrease of the density corresponds to an increase of the pressure. And so this region is able to balance the push of the gravity that is trying to squeeze it, but pressure reacts. And so there you get some sort of equilibrium between pressure force and gravity force, which is, in fact, if you compute from the solution what is the pressure to the gravity ratio, you find that it's 0.6, so about 1. So it's essentially in hydrostatic equilibrium, with the pressure sustaining the push that is coming from the entire envelope they're trying to get into the center. Okay? So this is the key point of that we have to keep in mind, because we will see why this is useful to determine the mass of the first stars. So now that was 1965. And many things have happened since then, but not so much. In the sense that people have tried to, because the 3D simulations are still impossible, people try to refine that single 1D study by including more physics. Remember that I told you that the key shortcoming is that that solution was for isothermal, for an isothermal gas. So people has released that assumption, and they've added in the study the energy equation. The energy equation is the same that we have seen before. So PDV work minus cooling. And in the cooling function, now we have all the things that we have learned in the previous lecture. So all the cooling from H2, for Compton cooling, chemical cooling, everything that you can imagine. And also they try to account in some approximate way for the fact that even if your exciting lines and the photons that are emitted are produced, they not necessarily are able to escape from the cloud. So the cloud could be optically thick, and that becomes true when the density increases and increases and increases. And so they try to catch in an approximate way by writing the optical depth as a function of some mean of the absorption times the size of the cloud. This is approximate. Radiative transfer is very approximate here, but it's there. So now this is the modern solution of the Larson-Penston equation, but now with all the energy equation involved. So we have 4 panels. A is the density. B is the velocity. They are the same 2 panels that I showed you before. Density, velocity. Here now we have also the evolution of the temperature and the evolution of the abundance of molecular hydrogen within the cloud itself. So the different numbers correspond to different stages of the collapse of the cloud. And you see that there's always this structure, r to the minus 2, and then a core. And the level of the density in the core constantly increases with time. And the velocity is also going down. And essentially, the gas that is coming to the, that is merging with the core then gets at rest. At the center, you see the velocity goes to 0. Okay? So you have a core and an envelope. So that confirms the Larson-Penston solution. It's valid even if it was obtained under approximate assumptions. However, we see that the temperature, that in that case was isothermal, instead has a very complex behavior. And what you're creating here, note that at the center, the core becomes very hot. Now the temperature in the core is 10 to the 5, while in the envelope here is still of the order of 1000 K, essentially the starting temperature. So why do you think that the core is getting hot? What's forcing the core to become hot? 10 to the 5 K. Roberto, don't move too much. Sorry? it's not a star yet. This is a collapsing cloud, but it's true. It's, we have, first of all, the energy to increase the temperature is obtained from PDV work. You're compressing something, right? And then when you compress, it gets hot. But at this point, because the cloud is opaque, even if you're exciting this radiation, these lambdas here that we have, the radiation cannot escape anymore. So this thing is adiabatic. So you put energy there by compression, and the energy cannot escape anymore. That's why, because the densities are now very high. We are talking here about 10 to the 20, 10 to the 25 particle per cc. Okay, so very high. So that is has become essentially an hydrostatic hot core. And this is where the star will form. Now, having confirmed this, we have forgotten something that cannot be catched by the 1D simulation. But you could, in principle, catch if you have a 3D simulation. And this is the process of fragmentation. Because for now, you're seeing that, for example, if you look at this slide here, you're seeing that the gas is accelerating, is going down, the velocity increases, and then it gets at rest, but nothing happens. So you go boom, and then you stop. But while you're collapsing, the gas could fragment in small pieces. So this flow can become incoherent. You form blobs here and there due to gravitational instabilities or other instabilities. So you have to look at the fragmentation condition. And sometimes actually in the literature there's a little bit of confusion, because I understand why, but there's a little bit of confusion between fragmentation and collapse. Sometimes they are referred to as the same thing, right? And in fact, in some sense, that's correct, because the fragmentation condition satisfies the same inequality that we were requiring for the collapse condition. That is, the cooling time is much less than the free fall time. So why is that? So first of all, let's try to understand in physical terms why the gas should fragment. And the answer is written here. The fragmentation condition is one for which the energy deposited by gravitational contraction, the thing that heats the core, makes it very hot, cannot balance radiative losses, and so the temperature decreases with increasing density. So if you're trying to squeeze the gas and the gas cools much faster than the density increase, then this is a condition that leads to fragmentation, because every single piece becomes independent on the global flow. So this condition can be essentially quantified. So the size of the fragments that form are essentially on the same scale as the Jing length. What is the Jing length? Is that size, as we have seen before, on which pressure exactly balances gravity. And you can show that the Jing's length, lambda j, is proportional to the sound speed times the free fall time. This is not what it, and you can understand it from the physical point of view that the sound speed is the velocity at which a pressure wave travels in the fluid. Okay? So you can only try to stabilize that structure if up to the point that can be reached by the pressure wave in a free fall time, so before the cloud collapses. Okay? So that's the scale that is exactly the product of the sound speed times the free fall. Now, in an adiabatic fluid, the sound speed, we can delete this. So in this case, Cs, we know is proportional to square root of the temperature of the gas. Okay? On this we all agree. And the temperature of the gas in an adiabatic fluid is proportional to the density power gamma minus 1, where gamma is the adiabatic index, okay? And so basically, if you substitute this into that, you will see that CS, as I was showing, it disappeared. Yeah, if you substitute this equation into this, you get the lambda genes is proportional to n, the density, to gamma halves minus 1. Because the free fall time, we know, depends on 1 over square root of density. So the fragments form on a scale that ensures pressure equilibrium, as we have seen before. This is the gene's length. And so the mass of the fragment, which is the density times the fragment cube if you have a sphere, or squared if you have a cylinder. So eta can be either 2 or 3, 3 for spheres and 2 for filaments or cylinders. So you have some expression that depends on density to power with an exponent that depends on, essentially on gamma and the geometry. But if you say spheres, n is equal to 3, and we are happy. Okay? So this is the mass of the fragment. So what do we do with this? So the fragmentation can start, but can also stop, because for 2 reasons. Remember the critical density that we decided before, that we defined before. So the critical density, when you reach the critical density during the collapse, then you reach this condition for which n it's the emission becomes proportional to linearly to the density rather than n squared, because we are approaching conditions for local thermodynamic equilibrium. So that's the first reason for which fragmentation stopped. Or the gas becomes optically thick to the cooling radiation, which is what we were saying about the core. Because these 2 conditions make the cooling time longer. In principle, even infinite if the radiation cannot escape. Okay? So the cooling time becomes longer than the free fall time. So whenever you get into this high densities, almost adiabatic condition, then fragmentation stops and you don't break the cloud anymore. And so the gene's mass, in other words, does not decrease any further with increase in density. So even if you increase the density, that blob would not fragment anymore, because it's supported, it's in equilibrium with the gravity. And so the condition is that we can use is that if we want that the gene's mass, which is essentially the mass of the fragment that we have computed, does not decrease with increase in density. So we have a condition on this power here that very simply results in the condition on gamma, okay? The adiabatic index. So the adiabatic index has to be larger than eta minus 1 over eta. That for spheres, if you put 3 here, it's equal to 4/3. And for cylindrical configuration, is gamma larger than 1. So the stop of the fragmentation occurs whenever this condition is satisfied. So whenever the equation of state, which is given by this, becomes stiff enough, and by stiff I mean large gamma. Remember, for an adiabatic transformation, gamma is equal to 5/3. For an isothermal, is equal to 1. So we want for spheres, we want to have gamma larger than 4/3. So whenever during the evolution gamma becomes larger than 4/3, fragmentation stops. And whatever fragments you have formed, you can't fragment anymore. So that sets the minimum size of the clumps that eventually could produce a star without fragmenting in subclumps. Okay? This is very important. So with just this simple notion that gamma has to be 4/3, we can go back now to the problem of the collapse of the cloud and say, what is the size of the fragment that I form whenever gamma becomes larger than 4/3? And this is very interesting, because this is shown in this figure here, which is very important. So we are back to the problem of the collapse of the cloud. So we start, this is busy. Let me go straight. I'll spend 5 minutes on this slide because this is very important. So if you have to remember something, remember this. So we have here different curves. I'll explain what they are. But they are showing the evolution of a collapsing cloud temperature as a function of the density. So the same plot that we were showing before, but instead of as a function of radius, we are now comparing temperature and density during the collapse. Good. So here in the top panel, we have 4 different curves that show the evolution of temperature versus density as a function of the metallicity of the cloud. So the amounts of heavy elements that it contains. And we have 5 curves that go from 0 metallicity, which is the top curve, 10 to the minus 6, which is the same as 0, 10 to the minus 4, 10 to the minus 2, and 1 solar metallicity. Okay? So it's in solar metallicity from 0 to 1. Very good. In the bottom panel, we have instead, as a function of density, the evolution of gamma, adiabatic index. We learn that whenever gamma is larger than 4/3, fragmentation stops, and the size of the fragment that I formed at that time cannot be broken anymore. So we can, during this evolution, we can follow temperature, density, but also gamma. So for each curve here, you have the corresponding curve here as a function of density for gamma. And so you see that the curves behave differently. Metallicity 0 and metallicity 10 to the minus 6 of solar are this curve which remain pretty constant. But there are these small dots here, the circles. The circles denote the point where gamma in the bottom panel becomes larger than 4/3. And so there are other curves that are the diagonal lines that indicate the Jeans mass at that density and that temperature. Okay? So you can say that whenever you are at the primordial abundance, this first circle here is sitting here. So the cloud stopped fragmenting early on, where the densities are relatively low, 10 to the 3, 10 to the 4. But the Jeans mass is 10 to the 4 solar masses. While you increase the density, at 10 to the minus 6, nothing happens, same thing. But when you go to 10 to the minus 4, now this point here, the circle, moves there. Because already the little amount of heavy elements that you have put there, all the species that we have discussed before, facilitate the cooling and therefore the fragmentation of the cloud. And so now you jump from 10 to the 4 solar masses as the size of the fragment that you form to 10 to the minus 2, subsolar. So in that case, you just move from 10 to the minus 6 to 10 to the minus 4 solar metallicity, and your cloud breaks down in several pieces. It totally breaks. Then as you continue to increase, the point moves here. Remember that this is 1 solar mass, and the solar metallicity, it reaches 1 solar mass. But it remains here, between 0.1 and 1 solar masses. But it's a huge jump from the primordial conditions. And so this is particularly important because they've led people to think that there is a critical metallicity for the initial mass function transition, which is located around 10 to the minus 4 plus or minus 1. Okay? So there is a gray zone there because it depends on the specific composition of the gas. If you have dust, you don't have dust, what type of dust. But it's clear that there is a very strong jump from here to here. So there is a kind of different mode of star formation that under primordial condition, the gas only produces large clumps, so cannot fragment efficiently in tiny bits as it does locally in clouds today. Okay? So if this is real, then this is what has led the people to think that the first stars should be very massive because they form into fragments that have large mass, 10 to the 4 solar masses. Now, does that mean that all the stars are 10 to the 4 solar masses? No. And now we'll see why. This is the end of the chapter 2, and then we go into the properties of these stars. So we have seen the POP3 stars forming 10 to the 6 solar mass halo redshift 30, and the fragments have masses of 10 to the 4 under primordial conditions. And there is this critical metallicity value of the order of 10 to the minus 5 that marks the transition from one mode of star formation to the local mode of star formation. And we have seen that the internal structure is made by a core that is essentially in hydrostatic equilibrium plus an acritic envelope. And this is perfectly consistent with the Larson-Penston solution. Now, let's make a step forward. So now,
Can I ask a question?
sure.
In order to cool the envelope, you need the dark matter, and then you drop dark matter altogether. So it's not playing any role? Or?
No, it's not playing anymore, but dark matter works as a collector initially to bring the gas from the background density, the mean density in the universe, to this virialized state, which is 200 times the mean. But then, while the dark matter, once it starts to cool, while baryons are starting to cool, they concentrate more and more toward the center. So they concentrate on smaller scales where the gravity of the baryons becomes dominant, and the dark matter remains more extended. So these halos collapse toward the center, the gas collapses toward the center, while the dark matter still remains where it was. So gas matter collects the gas from the mean density. Then the gas is there. It's able to cool. And when it cools, it goes to the center. And there, it dominates the gravity. So we have this structure. And now think that the sizes, I told you that the typical size, the masses of the halos are 10 to the 6. But a halo redshift 30 has a virial radius that is about 100 parsecs, okay? Roughly. Now, this thing that we are talking here is even much smaller than that. It's sub-parsec. So now we have a structure which is like this, which has the core and the envelope. And so these are the initial conditions. So now, let's compute what is the accretion rate of this envelope onto the core. Well, at least very simply, dimensionally, the accretion rate is nothing else. We can simply say that is equal to the Jeans mass, which is the mass of the core, divided by the free fall time. And so we are seeing that the Jeans mass is equal to the lambda j cube times the density, and we have the free fall time. But this is proportional to CS cube times rho divided by the free fall time squared. And so at the end of the day, you find the very interesting result that the accretion rate is purely proportional to the cube of the sound speed and nothing else, divided by g. So it's a very fundamental result. It also, you can also show that it's valid also for black holes if you substitute the speed of light with the sound speed. But so the accretion rate, it's CS cube. And so it only depends on what? Oh, temperature. Temperature. Remember that CS is this, right? Apart from constants, is only proportional to T to the 1/2. So the hotter is the gas, the higher is the accretion rate. Now, remember the first slide when I was telling you that locally the molecular clouds have temperature of 10K. Now, we have seen that with molecular hydrogen, you cannot go below 500K. So the minimum floor is 500 because you can't cool it with molecular hydrogen. but likely you don't even get there. So let's say that it's of the order 1000 K. The typical temperature that you have in the fragment is 1000 K. So if you substitute that number there, I'm using here 1600, but more or less it's the same. So you get that the accretion rate is 4.4 10 to the minus 3 solar masses per year. This number is about 1,000 times larger than what we observe locally. So the accretion rate on these primordial protostars is tremendous, it's super high. Okay? Now, how long would it take to form a 100 solar mass stars from this accretion rate? Less than that. 100, right? So it's less than 10 to the 5. So it's 2.5 10 to the 4 years. So it's 20 million years you have already built up 100 solar mass stars. And in 10 to the 5 million years, in 10 to the 5 years, you build up a 1,000 solar mass stars. Remember that all this, there are 10 to the 4 solar masses there that you can accrete. So in principle, you can get to 10 to the 4 in 10 to the 6 million years. So it's very hard to avoid the conclusion that first stars were indeed very, very massive. Now, this is the story for which, or the reason for which we think that the first stars were very massive. And so we can, but the key role is played by the accretion rate. So the accretion rate is high, and is high because the temperature is high, and the temperature is high because the gas cannot cool down purely with molecular hydrogen to low temperatures as we see today. So it's very simple. Now, under this condition, this is a protostar, okay? So initially, as we will see now, this is the place where the star will form. And so we'll go through a phase of a protostar that is described in the next slide. So here, what I'm showing you is the evolution of this core under the action of the envelope that is accreting on top of this. And so I'm describing the radius of this protostar as a function of its mass, therefore as a function of time as it grows, for 4 different cases of accretion rates. Okay? There is an uncertainty on the accretion rate. And so the number that we obtained before is this one, 4.4 10 to the minus 3. And let me call it the fiducial one, which is this curve here. Okay? But then, to see the effect, we can increase this fiducial number by a factor of 2, or decrease it by a factor of 2 or a factor of 4. And you see that there is a very well-defined behavior that we will try to understand better, and can be divided essentially in 3 phases. In the first phase, in which the radius of the protostar grows with mass, then as the mass increases, it starts to shrink. And finally, you get in another phase in which you can either start again to increase with mass, or it could be even something dramatic could occur, that is, the star is blown apart. And we'll understand why is that whenever you have very large accretion rates. Okay? So this is what it is. Let's try to understand this graph. There are 3 phases: adiabatic, Kelvin-Helmholtz, and ZAMS, which stands for zero age main sequence, or expansion. So let's see why this happened. To understand this, we need to introduce yet another time scale. This time has to do with stellar physics, and it's called the Kelvin-Helmholtz time. The Kelvin-Helmholtz time is described by this expression, TKH, and is nothing else than the time that it would take to the star to dissipate all the gravitational energy by radiating at the luminosity L star. So you see that this is the gravitational energy divided by the luminosity of the star. So that gives you a time. And so this is called the Kelvin-Helmholtz time. Now, if this time is much larger than the time scale of which the accretion from the envelope is refueling the matter onto the star, then and this accretion time is defined by the mass of the star divided by the accretion rate that we have computed, then if this time is much longer than that, the accretive material just piles up without cooling, and so essentially you continue to grow the size of the star because you're piling up material, because the star essentially does not react particularly with the luminosity. But at the center of the star, there is a luminosity wave that is trying to get to the surface of the star, and it happens when the Kelvin-Helmholtz time becomes equal to the accretion time at some point. So the star start to become luminous, and therefore the luminosity makes the Kelvin-Helmholtz time decrease below the accretion time. So you begin what's called the Kelvin-Helmholtz contraction, and there are some details here that we can skip, but the key idea is basically that the star starts to radiate away again the gravitational energy at a rate that is larger than the time scale on which it gets the fuel from the envelope. And finally, all this comes to a balance, and the star settles onto this standard 0H main sequence, provided that the accretion rate is not too high. Because if the accretion rate is relatively low, then the stars start to produce the nuclear reactions, and starts to produce start the CNO cycle, helium burning, and you relax into the 0H main sequence, and therefore to unique mass luminosity radius relation. However, if the accretion rate is too high, then the star is so luminous that it becomes super Eddington. And so the luminosity is so high that it essentially expels all the external layers before you can get to burn out to start the hydrogen nuclear reaction. So you're blown away, and essentially the star self-destroys. So in a nutshell, this is what is happening. But now the key point is the accretion. So you see that what's happening is very much dominated by the accretion. So this phase, but also this phase. So the estimates that we have made of the accretion rate are based on the simple formula that I told you before. But then people have studied also numerically, and compared to the 4 curves that I showed you before, the numerical value that is obtained from simulation is this one, which appears very much in the ballpark of the analytical estimates, and also show that it's not so high not to allow the star to form and settle on the ZAMs. So at that point, if this is the situation, so the star is not blown apart, the final mass of the POP3 star is purely determined by the ability of the star to stop accretion. So as long as there is accretion, it will continue to grow. So that's the only limiting factor to the mass of the star. So the next question we have to ask, what could stop this accretion? Because otherwise, the entire fragment, 10 to the 4 solar masses, could accrete onto the star. Okay, so in principle, you can form a star as massive as the initial fragment. However, we are not considering here that there are processes that could stop this infall to occur onto the central protostar. We have several processes that we know work in the local molecular clouds. And in particular, we know that in local protostars, the key factor to stop the accretion is radiation pressure. So you have the stars start to emit radiation, and because there is dust and heavy elements, there is an opacity. So the momentum of the photons is absorbed by dust, transferred to the gas, and the gas is evacuated so that it cannot accrete anymore on the star. However, we have a problem again because in a metal-free gas, we don't have dust, we don't have heavy elements, and so the opacity is very limited, essentially zero, even if not zero for reasons that I tell you later. The other possibility, so that does not work in primordial stars. Bipolar outflows are another way to stop the inflow that is seen locally, but it requires magnetic fields. Now, I'm not saying that, actually, we don't know whether there are magnetic fields at redshift 30, but certainly, at least from what we know from the constraints that we have from the CMB, they cannot be of a dynamical important strength, because already at redshift 3, we have upper limits of the order 10 to the minus 9 Gauss for the intergalactic gas, and therefore, at this strength, it's unlikely that magnetic fields can become a player, particularly at even higher redshift 30 or so. The other possibility is that we have this formation if the halo and the cloud is rotating. That is possible, and this is one interesting idea. Other things that we see working at low redshift is that in a cloud you usually don't form you can form multiple fragments because the size of the fragments are much smaller in present-day star formation, as we have seen. So you have multiple fragments that are stealing gas one from each other. So it's competitive accretion, what is called, by companions. But here, because the fragments are so large, they are essentially the entire amount of gas that you have in this halo. Remember that the typical halo mass that we have spotted as a host for the POP3 stars is 10 to the 6. Now, if you assume a standard cosmological ratio between baryons and dark matter, then you would say that in that halo, you would have 10 to the 5 solar masses of gas. So at most, you can find 10 fragments if you're lucky. But so, and probably they are very separated, so competitive accretion is not very efficient. So all these different difficulties that we have in all these possible ways to stop accretion have led to the idea that the primordial IMF could be top-heavy. So this strongly biased towards the formation of massive stars. And that, of course, are good news for what you will hear tomorrow from Pratica. Yes?
Sorry, I have a question.
Yep.
With radiation pressure, so there's no dust, so maybe that doesn't work, but what about Lyman alpha? Could that kind of replace the dust?
Yeah. In fact, I was saying, even though before I was saying that this is not exactly true, because indeed you have radiation pressure on Lyman alpha, from Lyman alpha. Totally agree, and this is a very excellent point that is in the next slide. But yes, so that could be a possible way to do it. It's very important. Yes, so I don't remember. Yes, I think that it's good news that we have massive stars, because this is exactly what we want to start, to have a kickstart at least for cosmic reionization, because you have a lot of massive stars, a lot of ionizing photons that stars produce because they are hot. So now let's consider for a second this possibility, which is the most interesting one. So if you have a disk, now first of all, we know that halos have a certain spin. There is a distribution of the spins of the halos, and this could be inherited by the protostellar cores. And in fact, in simulation, we see that rotations, the cores are rotating. They are about rotating at 1/2 the Keplerian velocity. And so if the gas mass reaches the star via an accretion disk rather than a spherical infall, then the optical depth in the poles decreases, right? And so in the polar caps, the photosphere, which is the region, the radius from which photons can escape from the stars, is the surface of the sun, where tau is equal 1. That strings to the stellar surface itself, to the physical stellar surface. And so we have higher fluxes of ionizing and FUV radiation. Now, these plots are very busy, but basically just look at this one, where it shows that it's so the star is located here. And so this is the distance from the star in the plane of the disk. And this is along the rotation axis. The red thing here is an H2 region. Okay, so because the photosphere is now exposed in the vertical direction, so you can produce a very wide H2 region, which creates a pressurized bubble here, and the streamlines of the gas cannot actually penetrate down to the star. And so if you put this constraint, then you have a limit on the protostellar mass as a function of the rotational velocity in Keplerian units, so the typical value is here, that is given by these curves here. So basically, you shrink down your maximum mass that you can reach to values of the order, this is 100, so this is 100 to maybe 200 solar masses. However, if in addition to the H2 region, you also add radiation pressure on Lyman alpha, so Lyman alpha radiation pressure, that Lyman alpha is produced by recombination of these two H2 regions. So these photons are also pushing the gas away from the star. And in that case, you get a curve which is much lower. It goes from, I don't know if you can see, but I'll read it for you. It's about 30 to 40 solar masses. Okay? So Lyman alpha radiation pressure is potentially a very important effect on the final mass of the star. So this is rather unknown right now. So we don't know how massive is massive. So for sure we say that's 20, 30, but probably could be even 100 or 200, because depending on the detailed description of these processes. So right now we don't know. The best that we have done so far in modeling this situation, in which we have, again, a disk which is sitting here, and this is rotation axis. So these are simulations that are showing different things. So this is, on the left, you see the temperature, and on the right, you see the density. Okay? So the protostar is sitting there. And then you, as a function of time, that you can read also as a function of mass. So this is when the star is 20 solar masses. This is when 25, 32, and 42. You see that there is this thing here, there is an H2 region. The gas is becoming hot, green and red, so it's 10 to the 4 K here. And there's our velocities that are going in this direction. The density is becoming lower, and as a function of time, this H2 region expands and opens up. And so basically, it at this point is so open that for the gas is almost impossible to get to the center. It's like creating a cavity, isolating the central star from the rest of the world. So you're quenching, you're suffocating essentially the fuel contribution to the protostar. And this radiative feedback determines the fact that the accretion rate onto the protostar drops. And so you see here what happens. So the red curve is the case in which we have no feedback. So suppose you allow the accretion to occur without the H2 region. And then when you turn on the H2 region, you get the blue curve. So at some point, the accretion rate essentially goes to 0. And of course, the value at which it gets equal to 0 is 42, right? We knew that. And so, yeah, so apparently, this is the best thing that we have so far. But truly speaking, we don't have a final answer to the question of what is the mass of the first stars. There will be more studies. Observations are starting to find evidence for, galaxies that are powered by very massive stars and very massive clusters as well. But it's unclear whether they are truly population tree stars. Then you can compute spectra of the stars, and you can design observables, but that requires another lecture, and I don't have time to go into that now. So I think I'll stop here, leaving you the recap of the properties that we have discussed so far. Just very rapidly, the masses are between 30 and 200. Of course, they are metal-free. The opacity is very limited, so it's only electron scattering because there is nothing else. Then they start to produce their nuclear energy starting from the PP cycle, but then turning into the CNO cycle. These stars emit incredible amounts of radiation because they emit at the Eddington luminosity, that is 10 to the 38 ergs per second, or 10 to the 40 if you take the mass to be 100. So it's about 10 to the 7 times more luminous than the sun. So a single star can make 10 to the 7 times more light than the sun. So this is truly impressive. So it's like a mini galaxy. And then, of course, they also can lose mass. And so the evolution of these first stars is studied, but again, we don't have conclusive results. And I think in the next future, we can both improve the theory, but also we hope that some new hints come from the detection of these first stars, not only in the high redshift universe, but also as remnants of this epoch for example, in the galactic halo, in the halo of the Milky Way, where we hope to see stars that are pop-tree stars, but with low mass that are still alive. We never found one of those yet, so that means that we have already some limits on how massive could be the how top-heavy could be the initial mass function. But we also have different techniques to try to spot them from the element abundance that we see reflected in metal-poor stars in the halo. This is stellar archaeology, but it's a totally different topic. So I think I'll stop here, and I'll get your questions.
Does the lifetime of these stars change dramatically from what mass stars that have sufficient metals, like pop 2, pop 1 stars?
Well, first of all, in principle, with pop 2 stars, you should have very, very few, depending on what is the IMF, stars at 100 or 200 solar masses. But if you have the lifetime is roughly the same. So 100 solar mass star, it lives 3 million years, no matter what the metallicity is, basically, because it's just you're irradiating that energy, and that's what you have, right? So this is very short. The issue is that the pop-tree stars, if they all tend to be 100 solar masses, they produce a cluster of these pop-tree stars, but then after 2 million years, they are gone. And so they are popping and disappearing. And so that is the difficulty that people that are looking for pop-tree stars, like Roberto here, are finding, because it's very hard to well, there are signatures because these stars are very hot, so they produce a lot of ionizing photons that in turn produce very strong, they excite very strongly lines like the helium-2 line of 1640. The thing is that this line is a signature of pop-tree stars, but lasts very shortly, this 3 million years at most, right? Then it disappears. So this is the difficulty. Yes? Yeah.
Coming back to dark matter, is the shape of the power spectrum such that you would not expect clumps of dark matter to perturb your forming star?
Sorry, I didn't get the question.
Would you expect to have clumps of dark matters within the region of interest which might disturb the...
No. Well, you can have maybe in the sense that you can have a substructure as you have, like in any halo, right? In the Milky Way halo, we know there are lower mass things. So if you have a cold dark matter spectrum, then you expect fluctuations on very tiny scale. So of course you can have tiny subclumps there that it could depend where they are located. You could have perturbations of the gravitational potential due to the presence of the clumps. On the other hand, when the baryonic collapse starts, the things become so compact that you go down to a few hundred AUs. And so on that scale, I find it hard to see that dark matter still plays a role. But truly speaking, it's an open question. Yes?
Generally, it is expected if there are some POP3 stars, they will be found. If they are detected, they will be detected at higher redshifts. But is it possible to detect them at lower redshifts as well?
Yes, there are two possibilities here. One is the one that I mentioned before. So people have been surveying the galactic halo of the Milky Way since 30, 40 years now, and try to find some purely metal-free star. They didn't find any. And the reason could be that if we are right and the IMF is all shifted towards large masses, these stars should be long gone, right, by now. If instead there are also stars that were small enough, and that means that less massive than one solar mass, they could be alive today, but we have not found them. So that already sets a lower limit on the IMF, one thing. The second point is that we can look for stars in a redshift 1, 2, 3, and they can still form if you have pockets of pristine gas within galaxies. So even in a galaxy like the Milky Way, if you find a corner of the Milky Way where the gas is metal-free, sure, you would apply the same type of arguments. The question is that it's very hard, they become very rare. And so, in principle, POP3 stars can form even today, provided you have a region which is sufficiently high density, but yet metal-free. And apparently, we never find something like this. I mean, all galaxies that we have never seen a galaxy which has such a low density to hope that there are some parts that are really metal-free. So it's possible, but unlikely.